Let's start working on chapter 7 and focus on alkyl halides and one of the reactions for them, which is called nucleophilic substitution. So first of all, let's see what is an alkyl halide. Alkyl halides, just like alcohols that you learned before, they can be primary, secondary, and tertiary. And they are composed of an alkyl group, the combination of carbon and hydrogen atoms, plus a halogen atom, fluorine, chlorine, bromine, or iodine. And alkyl group is combination of carbon and hydrogen. So, besides the primary, secondary, and tertiary alkyl halides that I'm explaining right now, we have some other alkyl halides. A primary alkyl halide can be simply bromine here. Why do we call it the primary alkyl halide? Because the carbon connected to halogen atom, to the halide, is connected to one more carbon, so it's a primary carbon. That's why it's called a primary alkyl halide. A secondary alkyl halide is connected, the carbon is connected to two more carbons. So if you have, for example, chlorine here, the carbon connected to chlorine, to the halide, is connected to two more carbons directly. So it's a secondary carbon and it's called a secondary alkyl halide. And finally, a tertiary alkyl halide is, I'm just using the simple alkyl halide just to show you how to categorize the carbons. So let's say you have a fluorine here. So the carbon connected to fluorine, to our halide atom, is connected to three more carbons. It's a tertiary carbon and tertiary alkyl halide. That's how you categorize your alkyl halides to primary, secondary, and tertiary. Besides those, you have some other alkyl halides. If the carbon connected to halogen, remember the halogen is shown in X. If your halogen is connected to a carbon on the double bond, is called a vinyl halide. So it's time to start learning these expressions. Vinyl, a vinyl carbon is a carbon of the double bond, directly on the double bond. The second type of halide, which is right here, is the carbon on the arene group, on the aromatic bond, which is connected to the halide. So it's called an aryl halide. Aryl halide. The reactions of these two are different. You won't study them here right now. Different reactions. Especially for aryl halides, you will learn them in organic too. So don't rush to learn these. The rest, if the carbon connected to halogen is one away from double bond, you see the difference between vinyl and this is the carbon connected to halogen is directly on double bond, but here you have a carbon away from double bond. So here you call it allylic halide. So allylic position, learn it, keep it in mind because you will need it later on. Allylic position is the carbon next to the carbon of double bond. This is called allylic halide. And finally, if you have a carbon connected to a benzene ring and connected to halide, the difference between aryl halide and this is that in aryl halide, carbon is the carbon of the aromatic ring. But for this one, which is called benzylic halide, the carbon is connected to the benzene ring, is not the part of the benzene ring. So you need to learn these terms: vinyl, aryl, allylic, benzylic. So later on, when we say benzylic carbon, means that the carbon which is connected to an aromatic ring. Which one is the aryl carbon? Is the one which is in the ring. So these two, allylic halides and benzylic halides, have the same reactions as the alkyl halides. Excuse me. Similar to alkyl halide reactions. Okay, so the next thing, now we know what is an alkyl halide, alkyl group plus a halogen. What are the different types of alkyl halides? Let's start naming them. And our focus is on just the simple hydrocarbons, simple alkyl halides at this point, because you will learn the rest of them later. So let's work on the practice on page 1 of this study guide. Or, you know what, let's work on C and D this time. Okay, there is a fluorine here. So you already know the naming rules for alkanes. Naming rules are very similar to alkanes, but here, if you remember, in alkanes there was no functional group, but here in alkyl halides your functional group is the halogen, or let's say this area, the carbon. I will talk about them in a second. So the first rule is determine the longest chain. And let me add it that the longest chain that has maximum number of substituents. So longest chain 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you go straight, and again one more time, longest chain is not necessarily straight. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is the longest chain, which is like a scorpion tail, is bent. But where do we start from the numbering? Always start numbering from closest to the first substituent. Here, either from left to right or from right to left, your first substituent is on the second carbon. So we need a tiebreaker. What is a tiebreaker? The substituent, which is alphabetically prior, comes first. Tell me, what is the name of this substituent? Isn't it a methyl? Or let me see. We just said, sorry, we just said this is the longest chain. I'm talking about, sorry, this longest chain. For a second I got distracted with this. Okay, so 1, 2, 3, and 4, and 1 and 2. So fluorine comes first because this was the longest chain. So let's start numbering. Alphabetically coming first. Which one comes first? This is fluoro. This is ethyl. And this is isopropyl. So which one comes first? E, F, or I? Alphabetically, E comes first. So it's on the 6th carbon. It's 6-ethyl. What comes after that? Fluorine, 2-fluoro. And don't forget, when you are naming your halide, it has to end in O. Fluoro, chloro, bromo, iodo. So this is the second one, and the last one was an isopropyl on the 7th carbon. 7-isopropyl. Don't forget to put a dash between every number and letter. And finally, you have 10 carbons. The 10 carbon hydrocarbon is called decane. All right? So that's how you determine the name of the alkyl halide. The longest chain, which is not necessarily straight, and then we start numbering from closest to the first branch, and of course naming is always based on alphabetical order. And we don't forget to put dash between every number and letter. The next one, I would like to work on D because it involves the stereochemistry. Each time you see wedge and dash, it involves the stereochemistry, so I want you to be careful about the stereochemistry of the compound. 1, 2, 3, 4. Okay. Now we have this, and we have this. Now, the longest chain is obviously the straight chain, but how to number from left to right or right to left? From left to right, the fourth carbon gets chlorine. From right to left, the third carbon gets the group. So which group is it? And it's an ethyl group, right? 4, 5, 6, 7, 8, 9, 10. Okay, again, we have 10 carbons. Now, which one comes first? C or E? Obviously C, chloro. But there is a stereochemistry involved. If chlorine is in the back and these two sides of the molecule are on the plane, so what comes in the front? Hydrogen. So don't forget the second rule. When hydrogen is in the front, you determine the rotation and then switch the letter. So this chlorine, what was the priority based on the atomic number? 1. Here, if you go atom by atom, you have carbon, 3 carbons, and then hydrogens, but you have 1 more carbon. So obviously this is the second group, this is the third group, and hydrogen is your fourth group. So whatever that rotation we determine, we switch the letter. So it is S, put it in parentheses. Where is S? On the 7-1 that we want to name it. What is on 7? Chloro, S, 7 chloro. And what else do we have? An ethyl on the third carbon. 3 ethyl. There are 3 carbons in the chain, so it's called a decane. So each time you see a wedge and dash means you need to take care of the stereochemistry of the compound as well. Some alkyl halides have common names like ethyl bromide, isobutyl bromide, tertiary butyl iodide. So depends on what you have, means that you need to take care of the common name. So if you're supposed to write the ethyl bromide, here you will see the importance of knowing the alkyl groups, the name of alkyl groups. Ethyl comes from ethane, so there are 2 carbons and they will be connected to bromine. So this is 1 carbon, this is the second carbon. No one is allowed to put the bromine here. You have to put the 2 atoms, carbon atoms for ethyl, and then the third, the second bond is for the bromine. Or if you have third butyl iodide, I hope you still remember them. If you don't remember them, means that you're failing learning a new language. So you have to go back and review them. You cannot pass any organic chemistry course without knowing the name of these alkyl groups. So let's take care of the tertiary butyl first. Butyl means 4 carbons, right? Third butyl means there is a tertiary carbon. This is the first one. So let's make a tertiary carbon out of it. 1, 2, 3. A tertiary carbon is connected to 3 more carbons. And there is an iodine attached. And we keep the octet valid with 4 bonds around the carbon. That's how you determine the name of common alkyl halides. The physical properties of alkyl halides. Physical properties. They are obviously different from alkanes because they have a higher boiling point than alkanes. Why? Because they are polar, right? Polar. Because you have R for alkyl and X. So there is always a partial negative charge on a halide atom. Why? Because they are more electronegative, and there is a partially positive charge on the alkyl group on the carbons. So this bond is always a polar bond. So the boiling point is higher than that of the alkanes without any polar bonds. And the boiling point increases by the length of the chain, by the size of the chain. For example, this chain has a higher boiling point than this one. Boiling point. Or increases with the size of the halogen. This compound with the same length of the chain. This compound, bromine, has a higher boiling point than chlorine. Which one has a larger size, bromine or chlorine? Bromine, because bromine is lower in the periodic table. As far as their solubility, again, because they have polar bonds, they are more soluble than that of the alkane. Up to like 4 carbons, don't expect that whatever number of carbons you want to have in alkyl halide has a good solubility. No. Up to 4 carbons, good solubility in water. Greater than 4 carbons, then you may need to think about some organic solvents. Soluble in organic solvents. These are the points that you need to keep in mind. And the last physical property is, it's their reactivity. I don't call it the physical property. This is going to be the chemical property, but the reactivity of alkyl halides, because of the electronegative halogen, you will see that they are electrophile on their carbon. And in the next video, when we talk about these about the nucleophilic substitution reactions, you will see that we are going to use this. And in the next chapter, we talk about elimination reactions. We talk about all these electrophilic carbon centers. So this is just because of polarity of the bond. It creates a good electrophile for a substitution reaction. Okay, now you know a little bit about alkyl halides. Let's talk about their substitution reactions. In substitution reactions, when the name describes, there is a substitution happening, like what you see here. What do you think has happened based on the reactants and products? It looks like this O has attacked this carbon, and the molecule kicked the chlorine out. And this is correct. In a few minutes, you will see the mechanism is true for such a compound. We are supposed to identify the substrate, electrophile, nucleophile, and leaving group, and then propose a mechanism based on comparison between the reactant and product. We propose this mechanism. Let's get familiar with some of the terms here. Substrate. Substrate is your alkyl halide. Halide is called substrate, the compound which is being attacked. So this is called substrate. In the substrate, what did I just say? The carbon connected to halogen. Halogen has a partially negative charge on it. The carbon connected to it has a partially positive. so makes it a good electrophile. Electrophile is carbon attached to halogen, always. Living group. Living group, we call it, let me just write it complete here. Living group, which we show in LG. LG is always your halogen. So here, chlorine is your living group. And why this change happens, why living group leaves? Because a nucleophile is going to attack the electrophile. And because we want to keep the octet complete, don't forget you have an invisible hydrogen here, then chlorine must be kicked out. So if you want to propose a mechanism to the practices on page 2, let's do it real quick. For A, for example, and we're supposed to write down the products. Which carbon we're talking about? The carbon connected, because this is our nucleophile, remember? This is our nucleophile. Nucleophile always has a negative charge. So the carbon connected to halogen is our electrophile. The attack is from nucleophile to electrophile. What is the living group that should be kicked out? Bromine. So if you want to write the product, is going to be OCH2CH3 plus bromide and the rest of the ions if we have any. The second example, let's work on D. On D, you'll have bromide, NaCN. Then let's determine our nucleophile. This is actually Na positive and Cn negative, right? It's an ionic compound, so our nucleophile is Cn. What is the electrophile? It's always a carbon connected to the halogen. So this is your electrophile. The attack is from nucleophile to electrophile. The halogen will be kicked out. So don't worry about this sodium here. Sodium is going to pair with bromine. So you will end up having Cn here plus Na and Br that form the new ionic compound. Okay, now we are closer to defining our living group and nucleophile and the rest of the terms. There is just one more practice here on page 3. We need to take care of page 3. Propose a mechanism for the following reaction. The final products are neutral. Okay, so for A, this is your nucleophile because it has enough electrons. A nucleophile attacks the electrophile. Electrophile is always the carbon attached to halogen. So living group, which is halogen, will be kicked out, and you will end up having, don't forget that you need to count the number of carbons, otherwise you will mess it up. How many carbons did you have in the longest chain? 1, 2, 3, 4. 1, 2, 3, 4, you still have it. Instead of the connection, the bond between carbon and bromine, now you have connection between carbon and nitrogen. If you're wondering you need to write the second product. The second product is not as important. The main product, this is the bromine that has been detached. And here, what type of alkyl halide did you have here? Primary. What type of alkyl halide do you have here? Why do I say primary? Because carbon attached to bromine is connected to 1 more carbon. Carbon connected to chlorine is connected to 3 more carbons, so it's tertiary. And it's added to water. In the next video, you will see that we talk about different mechanisms. So here, because it's so crowded in the tertiary alkyl halides, water molecule cannot get close to electrophilic carbon. So what happens is that the molecule spends some energy. It's a pretty slow reaction comparing to the first one, and the molecule kicks out chlorine first. So you will end up having this cation first, okay? And of course you have chloride here. And then water molecule attacks. Now there is enough space, so it will attack and it will connect itself. OH2, right? And if you calculate the formal charge, because oxygen has put this lone pair as a bond, there is a positive charge on oxygen. Learn it from now. Positive charge on oxygen cannot be tolerated by oxygen, because oxygen is an electronegative element, doesn't like a positive charge on it. So what happens? You have more water molecules in the container, right? It's not like you just pick one molecule and then dumped it in the reaction vessel. So the second water molecule comes to help the previous one. What happens? One of the hydrogens is grabbed and the charge will be stabilized on the oxygen. So the final product is going to be OH. And plus HCl, because you have H3O, right? Plus Cl, so you will have HCl and H2O. Don't worry about these. What is important is our main product. Okay, and what is left here before we actually start working on the substitution reaction is to talk a little bit about leaving groups, nucleophile, and the solvents. So let's work on it real quick. I know that you already have studied and you know it maybe better than me, but leaving group. Leaving group is not necessarily just halogens. So far our examples were about halogens, but later on you will see that you will have different leaving groups. So good leaving groups are weak, or let's say they're equal. They're weak bases. So good leaving groups are weak bases. Like, what are good leaving groups? Chloride, bromide, iodide, and also water molecule is a good leaving group. In organic too, you will learn more about water as the leaving group. But here our focus is on the halogens as leaving groups. So good leaving groups are chloride, bromide, iodide, and water. Across a period, the leaving groups are mostly on the right side, so water is better, for example, than ammonia, because oxygen is on the right side of nitrogen. Down in a group, the size matters. The larger the size, the better. So bromide is a better leaving group than chloride, and also across a period, we say H2O is a better leaving group than NH3 because of electronegativity. So bad leaving groups are, as you see, fluoride is not mentioned there, is fluoride. OH is a very bad leaving group. In organic too, you will see that. In order to kick out the hydroxide OH group, we need to change it to water from a bad to a good leaving group. And hydride and alkyl groups and NH2 groups. So that's about the leaving group. So keep in mind these are good leaving groups. As far as the nucleophiles, what was a nucleophile? The substance, the atom or group that contains lone pair of electrons or a negative charge. So strong nucleophiles definitely have negative charges, right? Strong nucleophiles have negative charges. Like what? Like A very, very good nucleophile is OH. And you see it in so many reactions. So actually OH is much better than H2O. What's the difference? Both of them have oxygen, but OH has a negative charge on it. And strong nucleophiles are generally strong bases. Strong nucleophiles, strong bases. For the living group, you saw the strong living groups are the good living groups are weak bases, but for the nucleophiles, strong nucleophiles are strong bases. Don't worry about what we say about steric effect. It's for elimination reactions. So strong nucleophiles, something like this is a strong base. When it's too crowded, when it's sterically hindered. Oops. So we have a strong nucleophile here because it's a small nucleophile. It can penetrate inside the molecule to attack the electrophilic carbon better. But here you have a big nucleophile, so it's a weak nucleophile, and you will see the mechanism is going to be different. It's not going to be the substitution. You will learn that it's going to be elimination. But wait until the next chapter. And the last thing we need to know about, these are the factors in substitution reactions, is the solvent. We have two different types of solvents. We have polar protic. Polar protic means having proton. Having proton. And polar aprotic. A in chemistry means without proton. So some of the polar protic solvent, as it's mentioned for you in the book, is water, methanol. So they basically, what is common in all of them is that they can form the hydrogen bond, right? Not against each other, with each other, just by themselves. They can form the hydrogen bond. And also tert-butanol, ethanol, ethanol, acids, of course, they're all polar and protic. So they can solvate, or they can surround both cation and anion. Polar aprotic solvents can only surround or solvate only the cations. They cannot form hydrogen bonds, like acetone and like dimethyl sulfoxide, or we just call it DMSO. You don't have to memorize the structure of these solvents, but you need to know if they are protic or aprotic. We just use their abbreviation acronyms. We never use their complete names. DMF, dimethyl formamide, and we also have HMPA, which is hexamethyl phosphoramide. Dimethyl sulfoxide is the most common. Also THF, tetrahydrofuran, is very common, and acetone. So these first three are very common. Polar aprotic. In polar protic solvents, iodide is better than bromide, for example, but in polar aprotic, bromide is better than iodide because stronger base and stronger nucleophiles. So based on what we learned, there are two types of substitution reactions for alkyl halides, SN1, SN2. After you practice enough on the basic concepts, we will start working on SN1 and SN2 reactions.